Welcome everyone to this PyMoDAQ video. So today I'm going to talk about a brand new extension, namely the PID controller. So just to recall in a few words, so PyMoDAQ has been built around a dashboard containing the control modules to drive your instruments, your actuators for your varying parameters, and your detectors for the data you want to measure. So obviously the direct application, direct first extension you're going to use is a DAC scan. But sometimes what you would like is to make a signal being as stable as possible, even with introducing some feedback control. So that's the purpose of a PID controller. So how is it working, this PID controller? So maybe you are familiar with it, but if you're not, then I'm going to introduce it in a few words. Well, let's say here you have a target value for your stability point, and I'll make an example in a minute. So then you're going to compare this target that you would like to achieve with some kind of measurement, and you're going to compare the two. You get an error from that. This is E of t. And then you're going to multiply this error, E of t, with different coefficients. We have the PID controller that stands for proportional P, integrator Y, and differential D. And each of them is going to add some features on your error, and you get like this a correction factor U of t. This U of t will be fed into a feedback. So it's something, let's say an actuator, that will introduce the correction so that your measurement will get closer to your set point, your target. And then you do that in a loop as often as possible, and eventually you will minimize the error E of t. So to make it more understandable, I'm gonna show you on an example. So here I've built one of my favorite setups using some small lasers, cameras, and so on. And you have the schematic here on the right of the screen. And basically you have a laser, a mirror that can be moved, tilted, let's say, with two piezos actuators. You can tilt the phi and theta angles, and you are going to measure the spot size, the spot of the laser on a camera. Obviously, when you change one of the piezo, the beam is moving on the camera. So for many setups in optics, you would like this spot on your camera to never move. Or if it's moving, you want to introduce a correction to make it as stable as possible. That's beam pointing stability. So this setup could be used to stabilize the laser going down to your experiment. And well, how to do that? So if I'm gonna show you the real setup, that's just here. So that's the exact same guy. We have so the laser, we have the piezo, the mirror that is on the piezo actuator, and then we have two detectors. We have one called the camera that will just extract the position of the laser on it. And you have also here a webcam that can just look at the projection of the laser on the screen. That would be your experiment, and you want the beam to be as stable as possible. All right, so let's try to first control this setup and then try to stabilize it. And I'm gonna start with a dashboard. So using the dashboard, I will be able to drive the piezo actuators and to measure the feedback signal from the camera. So I've prepared a preset for this. I called it beam steering real no model. And the different modules, control modules, are starting. So I have 4 modules. I have 2 piezos, one for the x-axis or theta tilt, and y for the y-axis on the camera or phi axis. And I've called them x piezo and y piezo. And then here you have your camera. So if I run my camera, I'm gonna look at the laser beam on it. And I can grab it continuously and showing you that if I move my piezos around, well, you're going to control the position of your laser on the camera. So that's nice. But what would happen if someone is touching your experiment, or if some heat effects or whatever is introducing some drifts in your beam pointing? So for instance, if I touch one of my mirror here, or there is some vibration, well, basically I can just make my beam moving around quite a lot. If I have a stabilization loop somewhere that is faster than my vibration, then it could just stabilize the beam in the middle. And that's why the PID module extension is about. All right. So now that I have my dashboard running, I can just get the data from the camera. So the data is an image here, but I can easily extract the center of the laser beam on the camera. This will give me a measurement for the X position and for the Y position vertically. I will compare that with 2 set points for the X-axis and the Y, for the X and Y axis, and then I will have 2 errors for X and for Y. I feed that into a PID controller, not a DIP controller, and eventually from that I'll get 2 correction values that I would have to introduce for my error to be minimized. And then I'm going to feed that into my actuators, my piezo actuators. So one for the X and one for the Y, and then start again, do a new measurement. Because I moved the Y and X piezo, the beam on the camera moved also, and so I can do a new measurement, compare it to the set points, and try to minimize the error. Loop after loop, I will eventually minimize this error and obtain well, a laser beam at the position where I want, and whatever the change that could happen on my beam pointing, my feedback loop will drive it back to the set point. So let's check that on our system. So I'm back here and on the dashboard, and now I'm gonna open the PID module extension and make my system stable or drive it using the PID loop. So when I open the PID extension, I got this new window with a few things. Here control buttons to drive the PID loop, and here some settings to enter values for my PID constants, some limits, and here a very important thing, it's a model class. So because of PID systems, because they are very different one from another, it was not possible to really make a general module just like this. So basically, for one time in PyMoDAQ, you'll have to write a bit of Python code to explain how your PID system is working. That's what I called the models of the PID module, and I've written a few of them here, and I'm going to load the one corresponding to my setup. I'm gonna do another video in a bit to explain how to write and set up a proper model. Okay, I init this model, and when I do that, the PID module is reading the content of the model, and there it sees that the model is defining two set points, one for x and one for y, and with initial values at 650 pixels 650 in both directions. Anyway, what happened now if I'm driving it, and I'm gonna to explain what's happening. So I'll run the system, and then as soon as I start the loop, open loop, I'm getting measurements. And these measurements are fed into the system, and here I can have a view of it. So basically here I'm seeing for my two channels, X and Y, the input, that means the measurements from my camera. So these two things are similar to these two numbers that are just there. And from these two measurements, the PID loop is calculating what should be the correction of the system here. At the moment, the loop is open, so these corrections are not applied to the piezos. As soon as I press this, unpress this pause button, then this correction will be fed to the piezo. And then the system is trying to correct and should go to minimize the error at the PID output. So if I'm moving around, you'll see that the measurement is getting there and stabilization happened there, while here the correction was getting very negative. So I applied -50 on the PID, on the piezos. And you see that there is some kind of saturation there on the correction applied. Well, this correction of -50 here is actually corresponding to the output limits I've applied in there. So if I go again in a positive direction, you'll see that the same kind of saturation appear them here at 50, that this guy. If I remove the output limit in the negative direction and I go to 400, well, basically, you see that the correction went down to -200. So I made a step of -200 with my piezo, which was quite a bit. Here I have a big overshoot. And then it introduced a positive correction to correct for this overshoot. And then somehow I achieved here a 0 correction and a target position of 400. So it means that by using these outputs, I can limit the magnitude of the correction applied to my system. So I can put some very tiny numbers and look at what's happening. It's taking here forever to get to my 600 set points. But because I'm doing it, I'm also allowing my system to change only slightly at each step. And sometimes it is what you want. You don't want your system to go like crazy and start oscillating around or even induce some very big change in your system. I have a nice example of that is when you are trying to stabilize interferometers. When you have interferometers, you don't want the steps in your interferometer to be too big. Otherwise, you will lose interference counting that you may need to infer the position of the interferometer. So you want an output limit to be at a certain value so that you can keep track of the change in your system. And it's then up to you to use it or not. So that's about the limits. Here, there is some other controls. Here, sample time, it's a time at which it's refreshing the PID loop. Well, if it can, if it's not limited by the measurements or whatever. And here, this 200 is a refreshing of the plots here. So that's mostly it for the different controls, and basically use these limits wisely depending on your system. you see that every time I'm changing the target value, the beaming is going there. So that's what you want for your stabilization. But obviously, it would be very nice to be able to drive your system at different positions and then stay there as long as needed, for instance, to make one measurement, a very tricky measurement where you need to be stabilized very well for a long time to have your measurements done. So what about using the features of PyMoDAQ for automatic scanning with, as actuators, these target points, these set points? It would be very nice if the DAQ scan could just say, okay, I want now my beam to move on to 400 and 650, stay there during the measurement of another parameter, and then move on to the next step of X and Y and do again a measurement there, and so on and so on. Well, that would be nice, and that's why I've done it. So we are going to switch off this and start again introducing the next level of this PID controller. So I'm gonna stop it here and quit it. And I'm going to close as well the dashboard and reload it with a tiny difference. All right, so here I'm back in my dashboard, and I'm gonna now load and modify the preset I was using just before. So it was this beam steering rail here. So I have it defined here. So you'll see that there is two actuators. There's X piezo, Y piezo, the camera, and there's even the webcam here that I didn't use yet. But in the preamble of the file, you see two things, well, the name of the file, but you see as well here the famous PID models I've talked about earlier. So here you can choose the one you want, and you can tell the dashboard that you want to use it, the PID, as actuator. What is it doing when you do that? Well, let's have a look. I'm going to load it again. So what do I see here? So in here now on this dashboard, there is two things on top. So there is first X piezo and Y piezo. And here there's also X-axis and Y-axis. So what are these? So we're going to illustrate that in a moment. But first, let's use the PID controller. So in here now you see that because I specified to use the PID model as actuators, he started directly the PID loading this model. And in the model, I told him that basically I have two set points called X-axis and Y-axis. And it created for me two like fake actuators that are connected to the set points of our PID controller. So let's start again where we were just before. So I initialize the PID loop and start the measurement, and I'm starting at this position 400 and here 650. And well, I just have to start it. So far, nothing different, right? Here it's doing things, moving around, trying to stabilize the system. But now I don't have to enter the values here because I have two actuators that could do it. So if now I'm entering here some positions, so I'm going to move that around so you see what's happening. All right. So now for X, if I told him go to 400, well, basically it's setting here the set point 400. And so the system is moving because the PID loop is running. Same for Y. If I want to go to 700, let's say, well, it's getting there. So it means I have now two actuators that will drive through the PID loop the system. So if I have two actuators, I can use all the other features of PyMoDAQ. For instance, the DAQ scan. So let's go back to a more central position for my set point here. And now I'm gonna load the DAQ scan. All right, so now I'm starting again the dashboard, and in that mode, now I have at my disposal two other actuators, and x-axis and y-axis, that can be used to drive the system using just standard things like the DAQ scan module. So you see here that now in my list of actuators, I can choose this x-axis and y-axis, and here, for instance, another detector, for instance, a webcam, that will give me some information on my experiment while the system is stabilized at each point that I want to be scanned. So first of all, I will add some region of interest here on the webcam so that I can live plot some information about the displacement of the beam around. That's it. So if I'll do that now, I'll have some information. And I'm gonna start the other bits now. So initializing here with some parameters, the PID loop, starting it and running it. Okay, so here it's at its start point, and I'm gonna do a 2D scan starting from this position here with some big steps so that we can see something. I'm gonna do 5 of them, and there will be 500 steps for in both direction. All right, so the PID is running, the acquisition here can start, and I have everything set up. So let's try it and run it. Okay, so the system is telling the PID loop to move around, and when it's achieved the right position to do the measurement. Of course, here my measurement is very quick, but you can imagine that it would be very useful if you have to do a measurement that is taking just like hours. And during this hours, you want your system to be as stable as possible, whatever happened on your environment. So that would be the perfect solution to do some usual scanning while using a PID stabilization loop on your system. And we can check here on the system that it did the right thing. All right, so basically, if I look around for what happened, well, my beam on the webcam just moved around. It didn't move quite a lot, so I'm not seeing it much. So I'm gonna zoom here and reduce it a tiny bit, the thing, and do it again while having an eye on the thing. Okay, ready? Start. So we're doing it again, and at each position, something is getting acquired while the system is stabilized. And you can see that my system on the camera is moving around as well. Okay, so my webcam is not the best signal ever. It's not moving much around, and but believe me that if you have a detector here, it will have a proper stabilization, and you can see it on the PID loop. Basically, on the PID loop, you can see all of the steps that has been done for the spiral scanning, and each time you have a PID stabilization step with some overshooting here, typical of PID loops, and here at the final position, you start again to stabilize at this position. So you can either do that or just fix the position and do some kind of monitoring of your signal while being stabilized. So you can use either the DAC scan or the DAC logger or whatever other module is at your disposal. Okay, so that's it for this video on PyMoDAQ here. So I hope that I've shown you how to use the PID controller, this new module from PyMoDAQ, and obviously there's still some mystery around with the model that you have to write, but this mystery will be soon enough solved with my next video, where I will show you how easy it is to write those models. Well, thanks for watching, and enjoy using PyMoDAQ.